All right. Welcome back, everyone. Math 154, Week 9, Lecture 1. Going to be closing out Chapter 8 today. As I had mentioned previously, Chapter 8 is a pretty short section in terms of content overall. It's really much more of a, I don't want to say existential section, that's not quite right, but more conceptual, understanding the importances between causation and correlation. But then there's a little bit of math involved that we'll be getting into today. But we will be picking up where we left off immediately with that Walmart guided activity that I had talked about very, very briefly before starting 8.1. And that's from the guided activities, like I said. But before then, let's talk about our whiteboard. So 6.1, 6.2, 8.1, 8.3 all have due dates. The 20th, today, obviously, the 22nd for 6.2, 8.1, the 27th, 8.3, the 27th. So both of those are due a week from today, since we'll be finishing both of them today. Then we have our Excel 6.1 fund that's going to be due on the 22nd, so that's right around the corner. We have our discussion board week 8 lecture 1 due tonight. Remember, that's our last discussion board unless I decide to throw a curveball up there, which I'm not anticipating. And then video quizzes 3 and 4 due on the 20th and 27th respectively. So final exam, just a little, I don't even want to say update because we did talk about most of these details last time. The final exam is going to be very, very similar to the midterm, with the sole exception that, well, two exceptions, we will not have class on the day of the final, and the day of the final is only going to be one day. The day of the final is the day of the final. So the midterm, we had 2 days. The final, we're only going to have one day, and that's because I'm not going to hold class the day of the final. We're going to keep it a little more traditional feeling. So we will finish everything that we need for the course by the 27th, and then you just finish up the 1 or 2 assignments you have left, work on your review, and then boom, you'll have the final on the 29th. So again, no class on the day of the final exam. That way, if you need the full 2 hours during class time, you have that available. So there won't be any kind of recorded lecture that you're responsible for watching, no extra assigned homework. Sorry if you hear my dog whining. But yeah, it's going to be the same format in that it's going to be 2 hours, 20 questions, and it'll take place in my math lab. You'll show all your work, you'll number your work, you'll submit it in Canvas. Again, all the rest of those details will be seen in the next lecture, as well as the one after that. I have reviews, plural, provided, and you're going to actually use the same review that you already used for the midterm review to study for the first half of the final. Remember, the final is cumulative. It's going to cover all of chapters 0 through 8, not really anything too crazy from chapter 0, but there could be an Excel question on the final, just like there could have been one on the midterm. So anything from chapter 9, we're not going to put in the final since we are going to be working on chapter 9, basically the class before and the week before the actual final. So it just wouldn't feel right throwing that on the final as well. So anyways, the review that was posted in Canvas for chapters 1 through 4 is still available, and I still encourage you to use that. There will be several questions on the final that will be similar to questions from the review. You could also study the midterm itself. Those 20 questions could have the potential to be similar to what's on the final in addition. I will also, if I haven't opened it up already, I'm trying to remember because I opened a bunch of things all at once. There will be a chapter 5 through 8 review available in my math lab. It should be available, but yeah, I did open this. I did open this. So you'll find the chapters 5 through 8 review in my math lab under the assignments, and I should have that at the very, very top. It should be the top thing you see, besides maybe seeing the midterm itself. And then once we have the final will be up there near the top as well. In Canvas, you will find the conversion formula sheet that you use for the midterm. You should also be able to find a new formula sheet, which will have all those crazier finance formulas that you may need a couple for on the final. And we've referenced that several times. You've seen it several times. I'm not going to pull it up again. You'll see it later today. I'm sorry, not today. Yeah, you will. You will. Had to think about where I was in terms of material for a second. But that being said, let's go ahead and pick up where we left off. Like we said, we're going to dive into that Walmart guided activity where we're going to talk causation versus correlation and get into some of the finer details of that. Here we go.
Okay, so let's get into Walmart. This is one of my favorite problems from the book. Again, these are all just examples, no discrimination against anybody, love everybody. So don't think we're just picking on obese people with this. So the spread of Walmart supercenters is linked to obesity, read the March 9th, 2001 Harvard Business Review Daily Stat headline. I mean, came from Harvard. Daily Stat headline. Jeez, I'm going to believe that right now, right? Well, yeah, in 2020, probably a lot of people will. And I'm not saying they wouldn't in the past either. But let's dig a little deeper. Caption went on to state, research suggests that one additional Walmart supercenter per 100,000 residents, and to give you kind of a scope, Portsmouth has about 100,000 residents. So if we added one Walmart to Portsmouth, which we did about, 7 years ago, not too far from TCC. So research suggests that if you add one Walmart per 100,000 residents, it increases an individual's probability of becoming obese by 2.3 percentage points. Oh man, they used percentage points. They know what's up. They know what they're doing. Clearly all of this is right. I mean, if you see the phrase percentage points, they have got their act together. No, the point of this is no. People like to use fancy language to make them sound smarter than they might be, to back up what they're stating. So, okay, you see percentage points and your brain might go, these are clever people. They know what they're doing. Just because you know a term doesn't mean you know how to link causation. Okay, so the researchers published in this journal say the study implies the proliferation, which means if Walmarts keep increasing in number and spreading over America or whatever country we want to talk about, of Walmart supercenters, which offer food at highly discounted prices. Also, I don't know about y'all, and I stopped shopping in Walmart about 5-6 years ago for various reasons. But when I was in Walmart 5-6 years ago and I'd go to Kroger or Food Lion, the prices were pretty much the same on like your normal packaged groceries. Now, your meat counter might be different, your seafood might be different, things like that. But I really don't remember seeing a massive difference in prices of specifically Kroger versus Walmart. Now, Harris Teeter I know is a little pricier if things aren't on sale. Food Lion's, kind of mid-range as well. But I remember a time when Walmart food was very, very much cheaper than the other places. I remember being in college and driving way longer than I should have to get to a Walmart just to save 30 or 40 bucks on my big grocery bill instead of going to the local store. And I just don't feel like taking that long drive would be worth it. Now there's more Walmarts, it wouldn't be a long drive anymore, but not the point of the story. All right, so they're claiming that Walmart offering cheap food explains 10.5% of the rise in obesity since the late 80s. So America since the late 80s and even a little further past than that. But we've seen our obesity rate, in other words, the portion of people that are obese in relation to all of the people, that would be the obesity rate. We've seen that number just consistently rise for the past several decades. Please read the caption carefully again and try to understand what the researchers are supposedly claiming. Chapter goes over the mathematics behind such statements. The caption is implying a causal link between supercenters and obesity. Namely, that access to mass quantities of inexpensive, unhealthy food at supercenters contributes to unhealthy weight gain. Supercenters are part of the cause people become obese. That sentence is not worded very properly, I feel like. Supercenters are part of the cause people become obese, is the claim as stated in the caption. This claim seems obvious, but having objective data takes us from the realm of speculation to science. So we're going to look at some data and see if we can link these together or not. Maybe there's something else going on. How much more do I need to read of this? Most definitely can point to a correlation. So there's definitely a correlation. You can very easily find correlation with a lot of things. Again, causation is the key. And we don't really focus a lot on causation in this course and the homework, but when you're outside of this world, when you're reading random articles on Facebook or, I don't know, whatever social medias post articles, Twitter, I guess. I don't really think Instagram really posts news. It's usually just pictures of food and puppies. I don't know. I'm making blanket statements about things I don't use. Just what I see from other people. So, in fact, the researchers are saying that if a city has 2 supercenters per 100,000 people and 6% of these people are obese, then adding another city with 3 supercenters, sorry, not adding, then another city per 100,000 people will have 8.3% of the population obese. They're saying every Walmart is causing about 2.3 percentage point increase. So that's why we went from 6 to 8%. Correlation does not imply causation. It doesn't disprove the researcher's claim of causation, but it does mean that one must carefully read the research. Again, confounding factors are the other possible factors that could cause the observed behavior. Maybe it's just the number of Walmarts are going up and obesity is going up. Maybe there's another reason that the obesity rate is going up besides Walmarts proliferating. For instance, maybe there are more supercenters built in poor areas, and it is true that obesity is higher in poorer regions in general. There is a correlation between the wealth of a region and the obesity rate of a region. Okay. I don't have the textbook pulled up. I have the workbook pulled up. That's okay. So all the same stuff was seen in here. I knew I was reading a lot of things I usually don't read. Okay. I kept looking for this stuff specifically. I was like, I want to do my weird statement. So please read the caption, blah, 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 blah. So previous headlines of this Harvard Business Review daily stat were mobile phone purchases reduce tobacco use in the Philippines. What? So somebody did some research and saw a correlation that the more mobile phone purchases someone had, the less they use tobacco. Or you could just say the more people that own phones, mobile phones, the less people use tobacco, and specifically in the Philippine region. So if you buy a phone, you're less likely to use tobacco. That's an interesting correlation, but do you think there's a causation there? Do you think your cell phone's making you not want a cigarette or something? I don't know. That just doesn't sound like a lot of sense. So then they had another article title, Thin Men Get Lower Pay Than Average Weight Men. Huh. Well, that's also weird. So if you increase your weight by 30 pounds, does that mean you're going to get a pay raise? I don't know. I just don't know. So maybe the last one, mobile phone purchases reduce tobacco use. Maybe it's just over time, people buy more cell phones, and over time, people have reduced their tobacco use because we're more consciously aware of the negative impacts of tobacco use on our lives, which are causation, not correlation. There has been research done on that, so don't argue over that one. The thin men get lower pay than average weight men. Well, guess what? As you age, you tend to get more weight on you. And as you age, you tend to make more money. You get better jobs or pay raises or promotions. So maybe it's just the younger people are skinnier and the older people are fatter, and the older people are making more money because of time. And then they do this nice little fun statement. This is my favorite. Apparently, men who are thin from smoking should buy an iPhone in Manila, that's in the Philippines, and move next to a Walmart center in order to get a raise. If you link all three of those things together, if you are a thin man and you smoke, and you don't make much money because you're thin, you should buy an iPhone to reduce your smoking use or to quit, move to a Walmart to get fatter, and then get fatter to get a raise. I mean, that sounds like some 2020 Facebook article, no doubt. Okay. So what's really going on? We've basically already talked about all this. They also talk about how all that precise sounding percentage points. Remember, percentage points is talking about a total change in percents. That was a phrase that we dealt with in 4.3 or 4. I want to say 4.4 very, very heavily. So when you have a total change that's, say, apples to apples, and then the percent change is percent, that's not a problem. It's when you have a total change where your data is percents originally, So we went from a obesity rate of 10% to 12%, for example. That would be an increase of 2 percentage points. You don't want to say 2% because when you do the percent change or the relative change, that's where you'd say percent, and you don't want to confuse yourself. So again, like we were talking about, they use the phrase percentage points. You might go, oh, they definitely know what they're talking about because they know their statements. First of all, they might use percentage points wrong. I've seen that misused in the news. Second of all, just because you use a term doesn't mean that you are using it properly. I can't tell you how many times I hear people use words improperly. Irony, 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 irony. So many people use irony as coincidence. Guess what? Was guilty of it for a long, long time. And then somewhere around 18 or 19 years old, a friend fussed me out over it, and I spent some time and I learned it, and now I get it right most of the time. Sometimes irony and coincidences are hard to tell apart. They could be both. But a lot of times irony and coincidences are not the same. Again, just because you say a word doesn't mean you know what it means. Okay. So let's get into some charts and how they actually were doing this analysis. Where did this information come from? Here is a chart with two completely different sets of data on it, and that is a giant red flag to me out of the gate. Charts should really only have one type of data in them. So just charting a number of apples, or just charting an obesity rate, or just charting percentages, or just charting a total number of people, something like that. We are charting with the dotted line slash curve slash whatever you want to call that, because it's kind of like two different bits. This is the number of Walmart supercenters, and these are tracked on the left heights. So when you're right here, where my mouse is, that means in about 1998, there were about 500 Walmarts in the United States. And I'm saying about because, I mean, it might be like 1998.1 or 500.2, something like that. But then also in 1998, I can switch to the other curve, this black solid one, and I can trace the obesity rate back in 1998. So in 1998, when there were about 500 Walmarts, the obesity rate was about right here, which if you trace to the right is 0.3 or 30%. So in 1998, based on what we call obese, 30% of America was obese, which means you are overweight by a certain amount, or your BMI, body mass index, is higher than a certain amount, which, first of all, obesity rates are calling some people obese that aren't. BMI tracks your size and like height versus your weight, basically, and a few other measurements. And you can have someone who is just completely ripped, solid muscle, maybe 300 pounds, bodybuilder, and on paper they could be obese because they have so much muscle that this is not accounting for. Now you might say, well, clearly the obesity rate is just terrible then because of all these bodybuilders. They make up a very small portion of the population and are not really messing up the obesity rate. There are still some people that are probably labeled as obese that shouldn't be labeled as obese, but I don't think that it's going to cause more than 1% error. If you just actually did it more appropriately, which is when you study how much muscle, how much fat, how much bone, all of these things a person has, which is a little more involved and why it's not done that way. They like to put people in water tanks. You might see some special scales, and you can get calipers and all sorts of studies. Again, I'm getting sidetracked. So the reason I don't like this two-way chart, if you will, this two-sided chart, is because somebody decided, or Excel decided, that the left side was going to go from 0 to 2,500 in terms of number of stores, and the right side was going to go from 0 to 40% in terms of obesity rate. Now again, maybe a person decided that because then the picture really paints a picture of what they're trying to demonstrate, and which is this causation. Excel probably picks it just because it can get all the data on one screen, but people pick things so that it will mimic what they're trying to go along with. Now, if I make the obesity rate of 40% down here, so 0 to 40% is all in this range, that means that this black curve thing, the solid one, would be all down here, and then the Walmart supercenters would be all up here. It would look like Walmart supercenters are just exploding, and the obesity rate wouldn't actually look that bad because it's only taking up a small chunk of the graph. It wouldn't even be anywhere up here. Oh, that's not bad. Well, actually it is, because it's just 0 to 40% is all down here. So it doesn't represent a great image. Or maybe you go the opposite way and you call where the 0.4 is 10%. So now the obesity rate looks like it's way higher than the Walmart supercenters. So again, the point is, this type of graph or chart with two types of data that have nothing to do with each other except maybe correlation, this is terrible and a great way to misinform or confuse the masses. Okay, so when you look at this, you see, oh, the obesity rate's going up over time. Oh, look at this, the number of Walmarts is going up over time. So clearly one caused the other. Now, well, maybe it's the rising obesity rate, maybe that caused the Walmart centers to proliferate. Who says it can't be that? Who says it can't be America becoming more obese and thus we need more Walmarts? Why is it more Walmarts are causing more obesity? You know, which way is the causation? And that's something else that people get backwards often. So how can we look at this picture, dissect it, and say, I don't think Walmarts are causing the obesity rate to increase? So let's check this out. I'm grabbing my real pen. I'm about to draw on my tablet unintentionally. All right. So this region right here is completely flat on Walmarts. And that's because Walmarts didn't really come around until 1988. Now, you might look at this graph and say, well, it doesn't really lift off the graph until 1993. This is about where it stops being completely flat and picks up. Well, why, if there were Walmarts in 88, why didn't you see a bump sooner? Well, because this is 500 Walmarts, so it's going to be really hard to demonstrate 1 or 2 or 3 when only up here is 500 of them. So why does it start being able to visually see the lift off around 93, 94? Because the Walmarts started in 88, they made a decent amount of profit, so they opened a couple more. So by 1993, there were 10. And then those 10 supercenters, they were doing so well that they were able to leverage that money to open up another 50 or so Walmarts, and then it just kept spiraling and spiraling from there. So it's a compounding effect. You use the money from your other stores to make new stores, then more stores and old stores make new stores, and you get the idea. It's the same as our money growing over time. So that's why in 1993 there were 10, but only 2 years later, there's 240 of them. And then another 10 years later, there's almost 1,700 of them. So they just explode. So look at what's happening when Walmarts are not proliferating, when they're not growing and growing and growing in number. Look at this. The obesity rate up to that point was steadily rising. It was very, very, very steadily rising. Now there's a small little bump here around 92. The slope does increase just a smidge, but that's a very minor effect. So before Walmarts were around, the obesity rate was already rising. That is the first clue that Walmarts aren't causing the obesity rate to rise, because the rate was already going up before Walmarts were really around. Then Walmarts explode onto the scene, but look at the obesity rate here. So now let's split it up here. When we have this explosion of Walmarts, if Walmart's truly causing the obesity rate to increase, this explosion of Walmarts should cause the obesity rate to increase. But this right here, this region, is pretty much the same slope as this region. In fact, it flattens out for a little brief moment around 2001, 2002. I don't know if it's a coincidence that Super Size Me came out around that time frame, which, if you're not familiar with that movie, it was Morgan Spurlock, I think is his name, ate McDonald's for a month and decided that his body didn't really like it, so he gained a bunch of weight. He had some minor health issues, but that was just 1 month, not years and years and years of it. So he's like, okay, I probably shouldn't eat so much fast food, which again, it was for science and entertainment purposes. So a lot of people may have seen that and said, I'm going to chill out on the fast food. And again, I don't know, maybe that's just a coincidence. Maybe it's correlation and not causation. I only bring that up specifically because I know I saw that movie back in college, and it made me stop eating fast food altogether for quite a long time, and I still haven't had McDonald's in almost 20 years. outside of one time because it was an emergency. Again, not the point of the problem, but I like little fun side stories. Okay, so this, again, the explosion of Walmarts, but then the obesity rate not really changing in terms of its slope. The rate of the obesity rate was not changing. So that says, I don't think Walmarts are the issue. All right, so let's clear our screen. Take off annotate, scroll down. Oh, no, next page. So what else is there? Well, here we go. The maps in figure 8.4 and 8.5, that's these. Well, 8.2, 8.3, 8.4, 8.5. I don't know why they say 8.4 and 8.5. I'd go 8.2 through 8.5. Definitely convey a visual correlation between high obesity rates and locations of Walmart supercenters. It's not always easy to see the differences between correlation and causation. And we'll spend this chapter, blah, 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 you get the idea. So again, here's another piece of data, if you will, that tries to imply that causation. So these are called heat maps, the top left, top right, and bottom left. These are heat maps, and they show the obesity rate based on color. So the cooler the color, a white or a blue, would be a lower obesity rate, and your hotter colors, your magentas, your pinks, your reds, those would be your higher rates. So then they say that a BMI of greater than 30 or about 30 pounds overweight for a 5'4" person is what they call obese. So average height of a woman, probably about 5'4", I'd guess. So 30 pounds for a woman. Men, average height's probably 5'10", 5'11", 5'9", some in that ballpark. So because of the increase in height, this is probably closer to like 40 pounds. And again, ballpark number, not the point of the story. So let's scroll this down now so we can see the numbers for the colors. I really want to have this nice and large like that, but I have to zoom out a little for a while. So here are the colors. So if it's white, that means no data, actually. I said that poorly earlier. I was thinking white meant 0 to 10 or 0 to 5 or something, but white means no data. So this was 1990, before the internet was really, proliferated. We're going to use that word today. So we didn't have data for Alaska because it's Alaska. No data for a few other states as well. So the rest of these, in New Jersey it looks like. That's weird. So most of these are very light blues or medium blues. So the obesity rates were under 10% or 10 to 14%. And it kind of looks like the East Coast is worst mostly, except Virginia. Then we get to 2000, and people were gaining weight. People were becoming more obese statistically. So now our light blues and medium blues have turned to dark blues, darker blues, and these kind of yellow colors, which I think yellow is between blue and red in terms of a temperature idea. It's a cool color, but it's not hot. It's not icy cold like a blue would feel like. So we got a lot of states in the 20 to 24% region now, especially on the East Coast, up to about halfway through the Midwest. And then a lot of states in the 10 to 20% between these other two blues, but no states are under 10%, it doesn't look like. Then by 2010, things are getting serious. We got a lot of these magentas and hot pinks and dark reds. So we're East Coast 25% up, West Coast a lot of the 20 to 24% ranges, but then also some of the 25 to 29. This bottom right one is not a heat map. This is just the density of Walmarts in the United States. So every blue dot represents some number of Walmarts. I don't want to say it's one Walmart. Let's just say it's some number of Walmarts. It could be 1, it could be 2 or 3. It says 1, but I don't know that this is super accurate because it's really hard to tell how many dots are in this little region right here, even if you zoom in super close. So I don't know. It's just kind of tough to say that that is the case. Also, I only see 2 dots in the Hampton Roads region in 2009. I'm pretty sure that one in Newport News has been there since at least 2009, and there's been more than one Walmart on the south side down here. So that's why I'm saying I just don't know that each dot is one Walmart supercenter. Anyways, so what they try and do is they put all these together, zooming back out, and they want you to correlate that Walmart's causing the problem. Walmart's linked to obesity, at least. Well, well, look at this. Where is the worst side of the country in each of these? And 90. And 90, it wasn't as big of a deal because there really wasn't any Walmarts. They really just expect you to look at these two. But you still could argue that in 2000. But let's just focus on the 2010. So in 2010, look at kind of splitting the country in half. Look at the left versus the right side. The left side, you don't really see a ton of these blue dots, which means there's not as many Walmarts. Well, on the right side, it looks like chicken pox. Look at all those Walmarts. So clearly, based on this, all these Walmarts are causing this super, super dark red and magenta. And again, that's what they're trying to convey to you. But it doesn't mean it's causation. It could just be correlation. It just happens to be that all these Walmarts are over here and the America is more obese over here. What it really tends to be is that higher density populations tend to be more obese and Walmarts tend to go in higher density populations. Who's going to put a Walmart in the middle of Montana where there's like 7 people living in a 10-mile radius? That would be silly. And if you live in the middle of Montana, I bet you're getting a lot more exercise on a daily basis than if you're living in some city area where you're driving everywhere. You're probably walking or biking or getting more exercise. If you're working on the farm, especially, you're. I was about to make a statement that had to do with another state, so I'm going to disregard that. Let's go to the Dakotas. Maybe you're climbing Mount Rushmore every day. All right, Mount Rushmore is not in Montana; it's in the Dakotas. Okay. But again, the point of this whole discussion is that these pictures are trying to paint a picture to make you think one thing is causing another. You could get into this really heavily now, like, hey, if you wear a mask, does a virus spread more or less? We have seen studies with air molecules, people coughing through a mask, and then we have petri dishes and look at them over time. We see this correlation between whether you should wear a mask or not based on how much is in that petri dish, on whether you wore a mask, whether you didn't, what type of mask you wore. And then you get a lot of people saying that, that's correlation, not necessarily causation. A lot of people might say that, hey, the virus is smaller than your cough particles or the water droplets. And you can get into all sorts of arguments, which is why we have a country of people, half of them don't want to wear a mask. Now, again, I'm not telling you should wear a mask. I'm not telling you what to do in this mask situation. But the point is, lots of things you can say A causes B, but you have to actually do some research to prove that, whether it be reading articles or actually doing the research yourself. But when you're reading these articles, you have to take them with a grain of salt. Lots of people make statements that are not true. They may have data to back it up, but there could be confounding factors that are really causing this. So it's not just Walmarts, it's the proliferation of all the different fast food places. It's the proliferation of cheaper bulk food. It's people eating meals out more than home-cooked meals. It's people not paying attention to our diets, and it's possibly being misinformed on what our diets should be. Now, I've thrown the possibly for 2 reasons there, because one, unfortunately, not enough Americans actually follow some diet. And when I say the word diet, I don't mean like you can only eat 1,200 calories a day. I just mean eating a regular amount of food every day that keeps your body healthy at a normal weight, not fluctuating, things like that. Also with good health benefits, blah, 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 blah. Sorry, something's going on at home and I just got distracted. Give me a second. Okay. But there are certain people, we have the food pyramid. Personally, I don't know how much I trust the food pyramid. I've done a lot of reading and research that says a lot of other things. And I'm not going to get into that information because this is not me teaching health science. This is just me saying I question things, you should too. I see a lot of arguments that meat's bad. Meat causes cancer. And then they do these studies where you have people that increase their meat intake and then they're more likely to get cancer, or they did develop cancer, things like that. But the problem is, a lot of the time when people do these studies on food-related things is they don't track everything. And I mentioned this earlier. Okay, their meat consumption increased. What about their sugar consumption? What about their plant-based oils? We're seeing some research now that these these canola oils and things like that, they might not be the best thing for our hearts. Saturated fat versus unsaturated fat. Eggs, good Lord, eggs. How many times have they been good for us, then bad for us, then good for us, then bad for us, based on some studies, based on correlation, maybe not causation? I don't know how many years it's going to take for us to get the science of health and what we should be eating down. I don't know that we'll ever have it down, honestly, because, in my opinion, there's a lot of confounding factors linked to genetics. And again, that's an opinion. You can find research that would link my opinion to that. But yeah, so I don't want to rant too much longer on this. I think you've got the idea so far. There's one more thing I want to point out from this section, and that is this page. This is, again, one of my favorites, just an article coming out from some people that you would probably trust constantly, but man, did they post a bad article. So in 2000, not that one, this one, the CDC announced in 2004 that obesity was the cause of 400,000 of the approximately 2.4 million deaths per year. So in 2004, we were having about 2.4 million deaths. And the CDC, the Center for Disease Control, said that about 400,000 of those 2.4 million. Now that's 17% rounded to the nearest whole. It's 16.7%, whatever. The 17% of deaths are caused by obesity. So they published an article or announced, whatever. However, so they said causation. Obesity is causing 17% of deaths. However, the CDC did not control for a very important confounding factor. Control means a neutral value, kind of like when I said, all right, if you increase their meat intake, what about the sugar? What about their vegetable oils, things like that? You would need that to be consistent. You'd need to have people of the same biological nature, from the same region, whatever, with similar genetic compositions maybe, or maybe you need to take everybody. Maybe you need to study 100,000 people, not just 10 people, that kind of stuff. So the CDC did not take in old age. Guess what? Older people tend to be heavier. We talked about that earlier in relation to skinnier people making less money than fatter people. Well, older people tend to be heavier. It's just natural. Even before obesity rates were climbing, you just gain a little weight as you get older. It's natural. So older people tend to be heavier and also tend to die in greater numbers than younger people. So after the CDC did more research, they looked at their findings, they did more analysis, more statistics, more of everything, bigger, faster, stronger, we can rebuild it. I don't know why I'm referencing that. Anyways, after they revised all of their information, their findings, their paperwork, they revised their estimate to 24,000 deaths being caused by obesity. That is only 6% of the original number they published. That is insanity. The CDC messed up so bad that the real number was only 6% of what they had previously published. Now, did they do that intentional? I don't know. This isn't what we're here to discuss, whether the CDC puts out false information or not. I know that there's a certain person in our country right now that has an opinion about the CDC and what they're putting out with data and whether or not we're going to continue to use that data. And I am not telling you to trust or not trust the CDC. It's not what I'm telling you. I'm just giving you information and having small laughs about it. But I just think that that is absolutely insane. They had a study where they said 400,000 people were dying because they were fat, And in reality, and I say in reality, I'm just saying in their updated study, who's to say this study is right, you know? I mean, if they did it wrong the first time, fool me once, shame on you, right? That old saying, and not the George Bush version of it. Why could I keep referencing presidents? Anyway, so the CDC revised it to 24,000, 6% of the original number. So it turned out that 94% of the people they thought were dying because they were fat were just dying because they were old. That's bad. Now you might say, okay, well, if this is the more accurate number, at least they didn't hide it. At least they did come and publish their findings, and that's awesome. That's great. You know, back in March, we were talking about maybe we don't really need masks. Maybe we do, and now people are saying we do. So there was some change there. There has been some revisions as we have more information, as we do better research. So sometimes these things are intentional, sometimes they're not. And again, I'm not saying this 400,000 versus 24,000 was intentional. Maybe it was an accident. Maybe they were trying to fudge the numbers. I don't know. So there's some more in here, but that's just the one I wanted to pick out since it was kind of related to the Walmart one, just dealing with obesity in general. So read the rest of those on that page in particular. Bivariate data, this is kind of what we were talking about with the picture having two, I'm sorry, this is similar but not the same as what we were talking about earlier, where you've got two different charts. One of these is based on the actual prices at the time of gasoline. The other adjusts for inflation. Now, when you adjust for inflation, that means there's going to be a bigger gap in these in the past. So gas might have actually cost 50 cents back in 1976, but when you account for inflation in our dollars now, it's more like $2.50. And then we had the gas crisis of the 80s and the 70s, and the price spiked in the 80s. So even though it only went up from like, I don't know, 60 cents to about $1.40 at its worst, if you account for inflation, it went from about $2.50 to about $3.75 at its worst. Again, thinking in terms of our dollars now. There was a lot of inflation in the 80s and early 90s, the mid 70s to like the beginning of the 90s more specifically. And we've talked about that. There's a correlation, maybe even a causation to the the fact that in the 60s or 70s, we no longer backed the American dollar with gold. We went off what we call the gold standard. So now our dollar is just, it just has value on hopes and prayers and dreams, basically. Fort Knox is not backing all of our dollars, that is to say. So again, the difference of these two curves as you move on, they become pretty much the same because the dollar value in 2014 wasn't really any different than the dollar value in January 2016. Even if we zoom in, we can see that these things are almost identical as we get really close to the present. And again, because inflation was so big in the 70s and 80s, that's why these are further apart. If we kept going back into the past, these would keep getting further and further and further apart. So I wanted to talk about the relation here. So this chart is the gas prices every single month from January 76 to 2016. So these are gas prices by month. Again, green actual, blue accounts for inflation. When you account for inflation, it doesn't feel like they move as much. We've always been around the $1.75 to $3 range when we account for inflation. So thinking in terms of an updated dollar. It definitely feels more significant when we were paying 50 cents in the past. But again, everything else was more expensive, so relative to everything else, it more felt like the gas was $2.50 a gallon. So what they do is, we're going to take all the data points, and I think they use the inflated ones. I got to confirm. Yes, so they use the inflated prices. And what we're going to do is we're going to chart them over here, or what they do, and the oil price per barrel versus the price of gas. So gasoline is refined from oil. You dig up oil from the ground, you do something at a factory, and you turn it into gasoline. So in January of 1988, here is its inflated price. And oil had a certain price per gallon then, maybe 50 bucks a barrel, maybe 30 bucks a barrel, I don't know. And then January of 2008, when we had that gas crisis because of a hurricane shutting down some pipelines, one or two of them. So gas went up to $4.20 a gallon, $4.25 a gallon, practically overnight. And then we had the economic crisis that just shut that down, and gas went to like $1.50 a gallon on average, really, really quickly. So again, oil per barrel was like 100, I don't know, 130 bucks a barrel here, and then all of a sudden it was only like 50 bucks a barrel or 40 bucks a barrel. That was a sudden change because we had an economic crash. Everything else after that's been pretty steady. These little ebbs and flows or peaks and valleys. Gasoline changes price with the season, basically. So that's what's happening there. It goes up and then it goes down, then next year it goes up, then it goes down. So winter months versus summer months, one tends to be higher, one tends to be lower. I'll let you try and figure out which one's higher or lower. Look at gasoline for a year and see if you can figure out when it's usually higher. So oil price here may have been super high, and then oil price here may have been super low, and then oil price was super high, and then oil price was super low. So what they do is they make a chart, and it's oil price versus gasoline price. Now, these data points are not ordered in time, and they really demonstrate that with these little purple bubbles. So they say this dot somewhere over here was the February 99 data, where oil was only $14.77 a barrel, and gasoline at the pump was $1.32 for a gallon. This dot over here was June of 2008, when oil was 136 a barrel, so that was probably around the storm time, and $4.39 a gallon, so it was pretty high. And then January 1981, so this is 2008, which is not the furthest in time. We were going up to 2016. And then this point over here is 1981. So over here on the left, we got a point from 99. Here's a point from 81. Here's a point from 2008. They're again just demonstrating that these are not ordered based on time. So this point right here may be from 1976. It might be from 2012. It might be from 1983. We don't know. But again, that's not necessary. We're just charting the price per barrel of oil versus the price per gallon of gas and seeing if there's correlation, and then maybe trying to see if there's causation. So time is not shown in this scatter plot. Caution. So what these are trying to do is say, okay, if you see one thing increase, does the other increase? And pretty much these points almost follow a linear trend line. And this black line right here is Excel doing a line of best fit. And that line is pretty close to all these points. Now there's some that are a little further removed. These are a little more isolated, but they're still not that far. It's not like they're dotted over here, and over here, and down here, and here, and here. These fit a trend pretty well, which means there is correlation. As oil price increases, gas price increases. And again, this has nothing to do with time. Oil price tomorrow could drop 50 bucks a barrel, and then we'd probably see gasoline at the pump drop a proportional amount. Now, maybe it does, maybe it doesn't. Again, it's correlation, so it's not guaranteed, but it's expected. And then there's an R squared here, which again, we've talked about briefly. We will officially put in the notes in 8.3, so very shortly. R squared measures how close these points are to the line of best fit. 0.96 is excellent. That says there's a 96% correlation, basically. So in other words, a change in oil price correlates to a change in gas price on a 96% efficiency. That's basically what's happening here with that number. And again, official definition coming in hot soon. So this shows there's definitely a correlation between oil and gas. Does it show causation? It absolutely does not show causation. Do I need to go to the next page? I do not. Okay. This does not show causation at all. Data points and graphs do not show causation. Causation is the science behind everything. Causation would be us saying that oil price increases causes gas price to increase because gasoline is refined from oil. If oil is more expensive, it's going to cost more to make the gas. Now you might say, okay, well, is this, are these proportional? If I double the price of oil, does the price of gas double? And that is not true, because there are other costs associated with converting oil from gasoline. You have employees to pay, you have buildings to furnish and own, and taxes to pay, and you've got holes to dig. So if one day oil drops to zero all of a sudden, gasoline would not drop to zero. You're not going to go to the pump and get free gasoline, because they still have to pay those employees. They still got to pay the rent on the building. They still got to pay their taxes. They still got to pay to dig another hole. They still got to pay to buy more equipment. So it's not directly proportional or anything like that, but there's definitely correlation. If one of them, if all of a sudden oil doubles, the price of oil doubles, the price of gasoline is definitely going to go up significantly. I don't know that it would double. Maybe it does a little more than doubling. Maybe it does a little less than doubling. There's definitely a relationship, though, as we can see. All right. So that is 8.1. So confounding factors, these are the often hidden variables behind correlation. The confounding factor for the oil versus gas is the fact that gasoline is derived from oil. So again, the graphs show correlation, but if you want to show causation, you have to start doing analysis and talk about the confounding factors, which again are the fact that gasoline is refined from oil. What's really causing America's obesity? I kind of started trying to get into that, but I didn't make any blanket statements because I am not a health scientist. I'm a mathematician. But it definitely seems like if I were to publish an article, I would try and show the causal factor being just an increase of sedentary lifestyle, as well as an increase to access to cheap, quick, arguably unhealthy food. And again, I'd have to do a lot of science to prove that statement. The graphs would be very easy to show correlation. I can correlate all day on that, but can I show causation? I'm probably going to need some PhD candidates to help me with science there.
All right, pardon that brief pause, just had to set up the next part of the lecture. Here we go.
So 8.3, we're skipping 8.2, we go right to 8.3. And this is the last section of chapter 8. And this one will be quick. Correlation coefficient. This is that R squared we have been talking about constantly, except, well, R squared isn't the correlation coefficient. R is the correlation coefficient. R squared is called the coefficient of linear determination. I will admit I have swapped these names before in my head. The good thing is that doesn't really matter. It's knowing what R squared is and interpreting that is important. So I'm not going to give you a test question. What is the correlation coefficient? What is the coefficient of linear determination? The test questions would be, what is this value of R related to? What is this value of R squared related to? So I say here again, see text examples for random versus non-random data. We'll get into that after we go over the definition. And I won't actually do see text. I'm just going to make some images myself. So R is the correlation coefficient. R is between -1 and +1. And did I write it in interval notation later? I do not, so let me write it to the side. So -1 less than R less than 1. R squared, which is literally just take the value of R and square it, is the coefficient of linear determination. Now in Excel does not display R. It only displays R squared. Honestly, I really do not care about the R value. I care about the R squared value. There's only one thing that R can tell us that R squared can't, but if you have the picture in front of you, the graph itself can tell you the thing that R was going to tell you. So in my opinion, R is unnecessary as long as you have the picture. R squared and the picture give you everything you need. Now, when you square a number, the basics of math is when you square a negative, it becomes positive. If you square 1, you get 1. If you square 0, you get 0. If you square negative 1, you get 1. So this number originally being between negative 1 and 1, when you square it, it can only be between 0 and 1. So R we call the correlation coefficient. It's the namesake of the title section, but R squared is what we're going to be much more interested in moving forward. We'll study R squared, but R squared is what we care about. I've brought it up since chapter 5 for math's sake. So the coefficient of linear determination, and this coefficient of linear determination, we'll get a better statement about that very soon. So R squared is between 0 and 1. So R, an R value of negative 1 means there's a strong negative correlation. When I say negative or positive, what I'm talking about is the slope of the data. So if your data does something like, why do I keep drawing all 4 quadrants? So if your data does this, whether it's really tight or really loose, this would be negative correlation. If your data looks like this, and again, no matter how tight or loose it is, if it's just trending upward, this would be positive correlation. So when we say negative correlation or positive correlation, we're talking about the line or curve of best fit would have a positive or negative slope. So if the R is negative, it means the slope of the line is negative. If the R is positive, it means the slope of the line is positive. That's a very easy thing to associate between them. The closer to 1 or negative 1, the stronger the correlation. So 0 means no correlation. So if you have something like this, it looks like the data is moving in an upward manner, but they're very far apart from each other. It seems like there's not a super strong pattern. So if I had a line of best fit in here like that, which I don't want to have the lines there permanently, but if that was the line of best fit, it doesn't look that great. And they're positive, so R is probably in the ballpark of, I don't know, maybe 0.5, 0.6, somewhere in that ballpark. Whereas if you had something like this, this is probably an R value of like 0.9, maybe 0.95 even. And I have a really bad judgment of R values, again, because we don't really care about the value of R. I care much more about R squared because it has a much more important connotation. All right, well, if you had them looking like this R value is probably going to be something like negative, I don't know, 0.95. And this R value, which seems to be all over the place, is probably about 0, because the line of best fit's not really going to predict anything. So again, the only real useful side of R is you get a sign, and that sign tells you the slope, whether it points up or points down as you move right. The 0.5, the 0.9, the 0.95, and the 0 don't tell me that well, actually, how well the data correlates. That I'm going to get this percentage statement, and these don't link to it. It's R squared that's linked to it. So R squared is the better value to use to describe weak or strong correlation. So what's the R squared? Again, it's between 0 and 1. So 0 still means there's weak or no correlation, or if it's like 0.1 or 0.2. The closer you are to 1, the more perfect the correlation is, or the stronger the correlation is. If it's 1, it's absolutely perfect. If it's 0.99, it's amazing but not quite perfect. If it's 0.97, that's amazing but still not perfect. If it's 0.8, I mean, it's okay. It's not perfect, but it's still good.
your ballpark. If it's 0.6, I wouldn't use that as a model. If it's 0.3, throw it in the garbage because it's absolute trash. Okay, so r squared being between 0 and 1, so your pictures. And let's just take this last one that was these last four, not all of them, some of them. So something like, I need to zoom out. This, as an r squared, this would actually probably be in the ballpark of 0.4, maybe even 0.3. I'm going to go 0.4. This last one probably should have been a 0.6. Again, R is really tough to judge because when you square a decimal, these numbers get further and further apart. If you square 0.6, you get 0.36. So 0.6 sounds okay, but really, again, the R squared value is what is the number that we're supposed to go based off of. And I'm not telling you the why. It has to do with that sum of least squares math that we don't want to get into because it would take us months just to talk about it. So that's not a great correlation. It's weak correlation. But it doesn't tell me whether it's positive or negative because we're talking about r squared. R squared of, let's go with this one, something like that. This r squared is probably about 0.9, maybe 0.91. And again, don't take this 0.9 as super accurate. It might have been like 0.95, but that's pretty good because the data is pretty tight. This would be strong correlation. The r squared is not telling me that the slope is positive. The third one, I got a little ridiculous on that other axis, looked more like this. This was very tight. So that r squared is probably like 0.98, which is very strong correlation. But I can't tell that it's a negative correlation based on the r squared. I have to look at the data and say, oh, that's a negative slope. That would be negative correlation. And then finally, just random points, whatever. This we said would be no correlation. So the r squared is probably like 0.01. No correlation at all. So that's us showing strong, weak, positive, negative correlations. And if you wanted to throw the positives and negatives in there, you can. So the first one would be a weak correlation, but positive. This one would also be positive. This one would be a very strong negative correlation. And I wouldn't say positive or negative if something's no correlation. So that gives us a better idea of what we've seen in the past when I've displayed these r squareds. All right. So when we were talking about slope, when we were talking about intercepts, we gave you sentences, these cookie cutter sentences that you could use to say, oh, the output is changing at a rate of 3 apples per 5 oranges, something like that. That was the slope statement. This statement gives us our correlation statement. This statement gives us our correlation. If you take the value of r squared and convert it to a percent, that's what this says. This thing that I have highlighted right here just says convert, why is that happening? R squared to a percent. Maybe if I click, there we go. So again, this right here, why does it do that? Those are the same thing. Saying to take your r squared value and multiply it by 100%, that's just moving the decimal right twice. That's all we're doing. I said, yeah, right twice. That gives us the percentage of correlation. So if you have an r squared of 0.4, that means there's 40% correlation between these two things. If you have an r squared of 0.91, that means there's a 91% correlation, which means if one thing changes, you'll be able to predict that with 91% accuracy, basically, in the other thing. And again, it doesn't mean causation, it's just correlation. So if you have an R squared of 0.98, that says that 98% of the change in the output is because the input is changing. And say caused. Well, I guess because that's kind of a weak word to use. Because the input is changing, the output is also changing based on observation. That's a better statement to say. So here's our sentence, and this R squared times 100%. Again, this right here is just you writing the R squared as a percentage. So using the numbers above, you would say 40% of the variability, or 91% of the variability, or 98% of the variability, or 1% of the variability, which would be bad. So let's use the third one, 98%. So in this graph, 98% of the variability in the output can be attributed to the variability of the input. Variability means changing. So 98% of the change in the output can be attributed to the change in the input. I'm not saying it's caused by. I'm just saying there's a link between them. There's a correlation between them. So again, using the third one, 98% of the variability in the output can be attributed to the variability in the input. The changing output is linked to the changing input at a 98% effective rate, basically. So let's go back to our textbook. And let's look at our gas versus oil prices. We had an R squared up there. They gave us an equation. I didn't really point out the equation, but this 1.07, this is our fixed cost. The 0.02, this is our variable cost. So basically what we're saying is every time the price per barrel goes up $1, gasoline goes up about 2.5 cents at the pump per gallon. The 1.07 says, all right, if oil was free, gasoline's still going to cost you about $1.07 due to taxes, paying employees, paying for rent in buildings, digging holes, equipment, et cetera, et cetera. But really what we're focused on is the R squared. We said this line fits those data points really, really well. There's only a very small section that it's kind of off. And because these are chunked so well together, the rest of them, the R squared was awesome. It's 96%. Let's just call it round as to the nearest whole percentage. If you move it right twice, you get 96.38%. So that's a 96%. This says that 96, let's go back to our statement and just hold on to that 96% number. 96% of the variability in the, now what was the output? That was the gasoline price. Can I do this? That didn't work. Oh, no, not that. Darn it. Hit the wrong thing. Sorry, I got to zoom out some so you can see everything. There we go. So again, the statement we make is 96% of the variability in the, instead of saying output, we would say gas price or price per gallon. So 96% of the variability of gas price can be attributed to or is linked to the variability in the oil price. So 96% of the change in gasoline price is linked to the change in oil price. That's the correlation. Gasoline prices at the pump have a 96% correlation with oil prices. Now, again, that's not demanding causation. Yes, there is causation here, but that's not the point of a homework or test problem with this. We will get into a couple causation problems with their multiple choice. Again, causation is really, really difficult to prove in the real world. So in other words, if oil price goes up $1, gasoline price is going to go up about 2.5 cents on a 96% probability, basically. Now what that means is maybe it doesn't go up exactly 2.5 cents. Maybe it goes up 2.4 cents. Maybe it goes up 2.6 cents. Maybe it doesn't go up at all. Maybe there's some weird fluke. But 96% of the time, if you increase the oil price by $1, you're going to see the gas price go up in the margin of 2.5 cents. Again, sometimes it's a little more than 2.5 cents. Sometimes it's pretty much dead on. Sometimes it's like 2.6 cents or 2.4 cents. It might be 3 cents, it might be 5 cents. It might be $1 because something really crazy is going on. But 96% of that correlation would be seen. This statement is super critical. Let's go back and have it all on the screen now. That statement is super, super critical. Very, 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 very critical. All right, what do we have? Time. Sorry, I'm looking for the assignment I want. It's 286. Okay. And that's it for the notes in 8.1 and 8.3. Pretty short sections in terms of notes. Let's go to the guided worksheets. This one on page 278. Please, on your own time, check this one out. This one's really, really cool. I want to give you the answers, but at the same time, I don't. Sorry, I'm thinking. I'm trying to compound how much time we have, how much I can do, whether I want y'all to I'm just going to go ahead and say the answers really, really quickly. So if you download this, it's much better than printing it on paper because then you'll have to type the link. So download the document, and then you can click these links, and it'll take you to a website. One or two of them, I think the links are dead now. They no longer work, so you wouldn't worry about that problem. But then they go on and show you a study with some data. Oh, no, I shouldn't have closed that. That's all right. That's all right. Download, assuming I haven't been booted yet. Perfect, because I'm probably getting booted in a couple minutes from my math lab. So this page, for each of the following situations, write down whether you think there's a true causal relationship or if there's just correlation, or if it's what we call spurious, which would mean no real relation at all. It's a coincidence. So shootings per day in a city versus the daily temperature in a city. And they go on to say that this is a possible causal relationship based on the data. And basically they say heat might make people irritable and cause shootings. So check out that information, see if you can maybe make that association. 2, divorce rates in Maine versus per capita consumption of margarine. Now, what is really interesting about this one, and the title of it actually gives you the freaking answer. U.S. spending on science, space, and technology versus suicides by hanging, strangulation, and suffocation. So this is something completely different, but look at how well these things correlate. They're moving and bending with each other, but do you really think these are linked to each other? No, this is what's known as spurious. It just happens to be there's a correlation. And look at the R squared. It's 0.9978. This is dang near perfect. But if you actually try and study a root effect, no, this thing is not causing that thing, or that thing is not causing this thing. Number of people who drowned by falling into a pool versus films Nicolas Cage appeared in. And we're not talking about the good films, we're not talking about the bad films, we're talking about all films. And look at how well these just happen to correlate. So some people spent a long time trying to find two things that have matching curves and then just slap them on top of each other. And these are two-way charts. You've got Nicolas Cage films labeled on the right, and that's the black curve, and then 120 drownings is here, 140 drownings is here. Why does this height represent the same height? We could stretch these or skew these and make it not look like correlation. But even though we make it not look like correlation, we still see a decent amount, an R squared of 0.66. That's okay. And that's because here it's going down, one thing's going down, the other's going up. They're kind of crisscrossing a little bit here and there, but there's still some correlation. But do you think that people drowning are causing Nicolas Cage to appear in films? Or do you think Nicolas Cage appearing in films is causing people to drown? No, that's not causal. That is spurious, S-P-U-R-I-O-U-S. And again, nope, that doesn't work. I'd have to hit back. The link that I clicked actually said spurious in the title. Per capita cheese consumption versus number of people who died by becoming tangled in their bed sheets. First of all, I bet you're really surprised at how many people die by becoming tangled in their death sheets.
Oh my, that sounds terrible. Please don't sleep in death sheets. There's your problem. Tangled in their bed sheets. Amazing correlation, 95%. One's not causing the other. Divorce rate in Maine versus per capita consumption of margarine, 99% correlation. Look at how well these fit. Look at how well these ebb and flow together. But I can tell you that people aren't getting divorced because of increased or decreased margarine consumption. Sometimes data just looks the same. Age of Miss America correlating with murders by steam. How do you murder someone with steam? I shouldn't laugh at that. I'm sorry. I just don't understand how you murder someone with steam. I guess you lock them in a hot room. Hot vapors, hot objects. The other stuff I get. I mean, hot vapors, kind of the same thing. Very low numbers. When the first time I ever saw this, I saw the death by bed sheet. I was like, oh no, what's this gonna be? But it's very, very low. I mean, this is insanely low. So again, correlation. Correlation, not causation. Total revenue generated by arcades versus computer science doctorates awarded in the US. Now you might say, oh, well, this is both, no offense or anything, but nerdy stuff. No, computer science doctorates, nerds. People in arcades, nerds. First of all, I'm not trying to be mean. It's a blanket statement. Plenty of people go to arcades that aren't nerds. I'm not going to say anything about this one, and I'm not using that nerd in the negative connotation. Hello, math teacher. So, okay, yeah, there's correlation, but I don't think there's that many CS doctorates at arcades. I'm going to say this is mostly younger people, and you're not going to have a doctorate before you're 24 years old, roughly, on average. Again, there's what we call outliers, which that definition was on the previous screen. Outliers being data that just doesn't really seem to fit very well. 1 or 2 data points. All right, so you get the idea. There's lots of these. Check that website out. It's pretty cool. We're going to hit back. And there's a few more of these. So number 2 is spurious. Number 3, greenhouse gas emissions versus Arctic sea ice extent, which means how much ice there is. And that's definitely causal. Check it out. Density of yoga students versus yoga studios versus obesity rates. We would say that's possibly causal. So like the last one, causal, definitely. definitely. But this one, I'm going to say possibly causal. And again, you can look at the data and you'll see some correlation. Then you just got to think, well, if you increase a number of yoga studios, should that drop the obesity rate? And that's why I say possibly causal, because yeah, if there's more workout places, there's more places that people can go to work out and maybe lose some weight. But you also got to consider economic factors. You also got to consider the density of the area. I'd say wealth is probably a bigger issue. Sale of winter boots at LL Bean in Freeport, Maine versus the sale of ice cream cones at the same store. Now, some people would say these two things have nothing to do with each other. I'm going to say it's causal, though. I'm going to say that one is affecting the other. And it's not that one is causing the other. There is a confounding factor causing both of them, and it's temperature. Not many people are buying ice cream when they're buying winter boots. Not many people are buying winter boots when they're buying ice cream. Now, yes, some people eat ice cream all winter long, nothing wrong with that, but we have massively increased ice consumption in the summertime. We have massively increased purchases of winter boots, the rate of winter boots purchases in the wintertime. So when winter boots are going to go up, ice cream sales are going to go down. And it's not people buying winter boots that causes the ice cream to go down. It's the temperature causing winter boot sales to increase and ice cream sales to decrease, or vice versa. So that's a confounding factor. Number of math PhDs awarded in a country based on average temperature. That's spurious. Average annual temperature by country versus average PSAT. They say possible causal because heat could lead to lower test scores. Because you can't concentrate because you're hot and sweaty. I would actually go against this in average annual temperature. I would actually link that more to an economic situation, because if your area can't afford AC for your school, it might not really have to do with how hot it is outside. Just your city has hotter schools because no AC. They are doing it by country, so it's a little more general at least. So that's why I still say possible causal. All right. Last thing I wanted to talk about, well, first of all, show you that definition that was on the screen, but I didn't talk about when it was on the screen. Outliers are data points that don't seem to match the others very well. So let's say you got a graph that looks like this. And then and maybe so these points right here fit the mold really, really, really well, no matter what we're talking about. But this point right here and this point right here, they just seem to be out in left field and la la land doing their own thing. Those would be outliers. They don't fit the mold. A lot of the times when people do studies, they'll completely exclude outliers. Now, they may exclude some, they may exclude all, they may include all, they may include none. It's variable depending on what people want to do with their study. Outliers can be an important thing to consider in your data because you might think something is a perfect model when in fact it's not perfect. It could be really, 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 really accurate, but because these outliers pop up, that means the model isn't perfect. Sometimes just random things happen. And again, we're talking about people, and we're talking about health, and we're talking about finances, we're talking about life expectancies. There's outliers. There's always outliers. When we talk about the average salary of a person, kind of a random thing to throw out here. I'll put it above the graph just because of that. Average salary of a US person is somewhere in the ballpark of, I think it's like $75,000. Let's just say it's $75,000. And you might go, holy cow, how is the average person making $75,000? That's because this is a mean. This is literally an average of adding up every single person who makes money and the people that don't make money, dividing by the number of people, and that's what we get, $75,000. This has tons of outliers, mainly rich people, the people that are making billions of dollars every year. These people make so much money that they throw off the average, I can spell average significantly. Some studies exclude the top 1%, possibly bottom 1% as well, to make equal cuts to get a more relevant average, maybe in the 45 to 50 ballpark. Alternatively, some studies use the median instead, middle value. So if you lined up all 300 million American salaries from lowest to largest, from $0, because there are people making nothing, to, geez, what's Elon Musk making now? I don't even know. It's either Elon Musk or Warren Buffett. They're one of the top two or three. So whatever their annual salary is right now. So if you line all of them up and you pointed at the smallest one and the largest one, and then you moved closer to the middle. So the next, on the left, the next person who makes a little more money, which is still gonna be $0. And then on the high end, you move down to the second most wealthy person of the year. As you keep doing that, eventually you hit the middle person, somewhere around the 150 millionth person in terms of the middle. And then you say that is our average salary. Now, when you do that, that's another way of kind of ignoring the top 1% as a major effect. So when you think of a median, those top 1%ers, as you move from person to person to person, they have the same effect as moving from a person to person to person, making $40,000 to $40,001 to $40,002, which there are way more. And the median is in the ballpark
of, I want to say 40K. I'm not going to take the time to look up these numbers since we only have a couple minutes left. But those numbers are in your textbook or worksheets at some point. We have mentioned them in the past. So again, a lot of statistics have outliers. Whether we use the outliers or not depends on the point of the problem. We may not be allowed to exclude outliers. We may have to have them depending on the study. We may want to use them to show, I mean, it ain't perfect. Maybe we want to use them to make people think that it is perfect. So you just throw data away. That sounds like a great idea, right? Humana. I think that's going to be good. I wanted to at least show a couple of the guided worksheet activities, just at face value. I'm trying to get to the end point of the course that I want to be, so I have been skipping some guided activities here and there just to get you your information. So here's a graph with a mediocre correlation. So about 60% of the change in minimum wage can be attributed to the change in the percentage of hourly paid workers at or below prevailing federal minimum wage. So what's interesting about this problem is that it feels like the higher the minimum wage, the worse off we are. This is more because minimum wage keeps going up over time, but not quite enough to really have a sustainable income, a livable wage. But that's only a 60% correlation. That's good, but it's not great. And you can see the good, not great aspect of this. Here's one dealing with humidity versus temperature. So typically, the hotter it is, the more humid it is, but this is not true. And I really hope that they did this study in one region, because if you compared, say, the Virginia Beach or just Hampton Roads region to, say, the middle of or the southern part of Arizona, Arizona might be 100 degrees and have a humidity of 2%, whereas we might be 90 degrees and have a humidity of 100%, like all of last week. Good Lord. But if you just look at one region, its humidity index, which is a percentage of water content in the air, versus the heat index, which heat index is the temperature felt. And I'm sorry, that's what it is. It's heat index, not actual temperature. You can see up at the top, it says actual temperature. That does enable it to look across all regions. I'm trying to go too fast, so I missed a piece of information. I have to pay attention. Okay, so heat index. The hotter it feels, the more humid it generally is. The hotter it feels, the more humid it generally is. So if it's 80 degrees with a super low humidity, it probably feels like about 80. But if it's 80 degrees and there's a super high humidity, that's when it starts feeling like 90 degrees. So this accounts for Virginia, this accounts for Arizona. You don't have to go to a region. And this has a 98% coefficient of linear determination, a 98% R squared, which means 98% of this correlation, or of the correlation is up to 98%, excuse me, 98% of the change in heat index correlates to the change in the humidity, the relative humidity. Here's that gas versus oil prices again. We've already talked about that. Here's another one dealing with index of exposure to plutonium versus cancer deaths per 100,000 people. And we see that it seems to be increasing. We don't really have a gauge of what index of exposure means. We're not studying this. But these are a scary amount of deaths per 100,000 people. It's not super high, but you don't want to see any of them. There's an 85% correlation. So it seems like plutonium causes cancer. But again, I'm not saying it causes it. It seems like it. There's definite correlation. We'd have to do some science to get the causation. Here is a chart of the miles from Albany, New York, to the price of a toll. And somehow this has absolute perfect correlation. I feel like these numbers were probably fudged, or that the concept is something a little different. So this is different tolls.
I just don't feel like these tolls would correlate so perfectly. So I don't know if this data was fudged or if it's real. There are tolls or fees you can pay on things based on how far you go. Like if you go to DC, the last time I went 10 years ago, how far you go on the subway determines how much you pay. At least it did 10 years ago. Now I know that other cities like New York, it's just a flat fee. But anyways, this is perfect correlation on what your teacher suspects as made up data, but he has not confirmed that. It just seems like the further away you are from Albany, the more you're paying in tolls. I'm going to guess they probably started heading towards New York City. I don't know. I just know there's expensive tolls that way. Per capita, here's the chart for consumption of margarine versus divorce rate with that 98% correlation that we saw earlier. Look how close those dots are to the line. But again, that's correlation, not causation. Finally, the one I wanted to show, I'll look at this one. Now, all these dots do seem to be going in a positive manner. They do seem to be going positive slope, but they're all over the place. This line is not near the majority of them. Look at that terrible R squared, 13%. This is actually a really fascinating one. It shows that the predictability of winning or losing is not really correlated to a strength of schedule, which is basically putting a number 1 team against a number 64 team, a number 2 team against a number 63 team, seeding, if you will. And then the R squared does not just deal with linear trend lines, it also does with exponential trend lines. This is an exponential decay trend line. So this was people trying to memorize a string of letters. Like if I said memorize QRZT, you go QRZT. That was easy. 4, I can do that. But if I said memorize QRZTAC, that might be a little harder, but most of you could still probably do it, 100%, QRZTAC. But as I say QRZTACB, maybe a little less memorize it. QRZTACBD, I'm just keeping this easy for myself, a little few memorize it. But then between 9 and 10, all of a sudden, this gets really hard. And we go from about 60% of people being able to remember it to about 20% of people being able to remember it. There's a drastic jump. And it's not like all of a sudden people have an easier time remembering it, which is why they don't do a linear trend line for this. They actually do an exponential because of that drastic jump. Drastic changes, we tend to see exponential models. But even then, it doesn't look like it fits that well. But in actuality, because it predicts these later 3 pretty well and at least one before, this R squared is 88%. 88% of the correlation of people being, 88% of people being able to remember these is correlated to the length of string of letters, or is attributed to. Now, first of all, this curve sucks any sooner than 7 because you can only have 100% of people memorizing things. So this curve is just complete trash before 7 letters. And then it's okay after. It's not so great for 8 or 9, but it's definitely going to be good for 13, 14, 15, 16, 17, 18, 19 letters, in which those numbers are going to be ridiculously low. So even though you might say, if you try to guess the R squared here, I'd probably guess it in like the 75 region, maybe 78 region. It's actually 88. There's a little more room, a little more wiggle room with exponential models and small amount of data points. So when you start having tons of data points, that your R squared can get wacky. Or they're just all over the place with just a few data points. And do we have an exponential growth? I don't think we do. That's okay. This is all statistics. We don't need to do that. So bye-bye.
So that will close out the day. As I said, we finished 8.1 and 8.3 today. So those are going to be due in 1 week on the 27th. Then we also assigned video quiz 4, and we briefly mentioned the final exam, which again, we'll talk a little bit more about next time. But besides that, per usual, if you have any questions, please email me. Please make sure you get all your assignments done. Please start studying as hard as you can, invest as much time as you can in studying for this final so we can do awesome and make it out alive. If you have any questions, email me. Have a good day. Take care, everybody.